Hi, hello everyone, and thank you for joining us today for our webinar, Industrial Internet of Things, Protocols for Autonomous Mobile Robots. Today we're presenting the main protocols used in connected manufacturing environments to optimize autonomous mobile robots, coordination, scalability, and reliability. I would like to introduce our speaker today. Please join me welcoming Mark Carrier, Principal Engineer at RTI, leading the RTI's industrial automation efforts. As a technologist with over 25 years of experience, Mark brings a combination of deep business and technical expertise to help customers identify and solve their challenge. My name is Irene Aguilar, and I will be your moderator today. Just a couple of housekeeping notes before we start our presentation. Remember to leave any questions in the dedicated tab, and please take a moment to look at the webinar attachments where you can find some interesting content and also the webinar slides. So moving forward, I pass the ball to Mark, and you can start your presentation.
Okay, great, Irene. Thanks. Well, hello, everyone. And as Irene said, my name is Mark Carrier, and I'm a principal engineer at Real-Time Innovations. I just want to say thanks, everyone, for having the opportunity to speak to you today and share our thoughts on IIoT protocols for AMRs. And before I begin, I just want to say there's a famous quote from Alan Kay, a computer scientist, that says the best way to predict the future is to invent it. So hopefully you learned something from here as you're inventing your futures in AMR. So before we get started, I want to tell you a little bit about Real-Time Innovations. RTI is the leading vendor of products which are compliant with the Object Management Group's Data Distribution Standard, or DDS. RTI is the best in the world at ensuring our customer success in deploying production systems with over 2,000 design wins. So RTI software also runs on over 250 autonomous vehicle programs. We control the largest power plants in North America. We coordinate combat management on US Navy ships, and we drive a new generation of medical robotics. And RTI has a global footprint, which reflects our commitment to customer success. RTI's worldwide presence includes our offices in North America. We're headquartered in Sunnyvale. We have an office in Spain, and an office in Denver, and an office in Singapore. So with that, let's start. So autonomous mobile robots are poised to revolutionize the world by transforming industries, increasing efficiency, and enhancing quality of life. And these innovative machines are already reshaping manufacturing, logistics, and healthcare with their ability to perform repetitive, precise, and often labor-intensive tasks with speed and reliability. And technical innovation is fueling the AMR expansion, so particularly from gains in AI and advanced data management. So as the technology continues to advance, AMRs are anticipated to have a profound impact on various sectors from agriculture to smart cities, and are ultimately driving economic growth, improving safety, and fostering a more connected and automated world. Now, the complexity of building an AMR lies in the intricate integration of software and hardware components, encompassing sensor fusion, localization, path planning, control systems. So an essential aspect of this complexity is the need for a robust and efficient communication framework which can facilitate real-time data exchange and coordination between the various subsystems, and ensuring that the AMR operates reliably and safely in dynamic environments. So what protocol should I choose? So selecting the right IIoT protocol for an AMR is a critical decision that should be based on the specific needs and constraints of the application, as well as the broader ecosystem in which the robots operate. And that choice should be made carefully to ensure that the protocol aligns with the operational requirements and constraints of the AMR in the given industrial settings. So what protocol should I use? Well, before I can actually pick a protocol, it's important that we understand the requirements. And then we need to determine which type of network architecture will support those requirements. And then we need to understand the strengths and weaknesses of the various communication models to implement our network architecture. So really, it's a combination of our requirements, our network architecture, and our communication model. And that will guide us to the right choice for the best protocol. So building an AMR is a complex task, and understanding the requirements before building an AMR is crucial to ensure that the robot's design and capabilities align with the specific needs of the intended application. By doing this, you can avoid costly and time-consuming redesigns, and properly assessing requirements also helps in selecting the right sensors, software, and hardware components, and then optimizing the AMR's functionality and maximizing its potential value in its designated role. So let's just look at a few key requirements of an AMR. So AMRs require real-time or near real-time communication for navigation, obstacle avoidance, and coordination. AMRs often operate in crucial industrial settings where reliability is paramount. IIoT networks can have a large number of AMRs and other connected devices. So the protocol should be capable of handling a scalable network with the ability to add or remove robots as needed. And in industrial environments, there may be a mix of different robots from various manufacturers, different sensors and control systems. And an IIoT protocol should support interoperability to allow the different devices and systems to communicate and work together seamlessly across the network. AMRs can be vulnerable to cyber attacks, so security is crucial. So the protocol should include strong encryption, authentication, and access control mechanisms to protect the robot and the data that they generate. And depending on the specific application, certain data transmissions may require higher priority or guaranteed delivery. So quality of service features in a protocol can help ensure that the critical data is prioritized appropriately. And to enhance reliability, that protocol should also support redundancy and failover mechanisms to continue operations in case of a network failure. And lastly, it's beneficial that this protocol adhere to recognized industry standards to promote compatibility and ease of integration with other industrial systems. So now that we understand a few of the requirements, it's time to look at the different types of network architectures that exist and how they can actually meet those requirements. So the right network architecture is critical for ensuring that a solution operates optimally, securely, efficiently, and reliably. And in the network architectures, we really have three. There's centralized, decentralized, and distributed architectures. And each offer distinct approaches to meeting these requirements. So centralized systems typically rely on a single control node or data repository, and they excel in providing a unified view of operations and are relatively straightforward to develop and manage. However, they do struggle to scale efficiently. They face single points of failure, and they can be less adaptable to rapid changes or future-proofing a system. If you look at a decentralized system, as its name implies, you don't have one central owner. Instead, you have multiple central owners, and each of which usually stores a copy of the resources that users can access. So a decentralized system can be just as vulnerable to crashes as a centralized one. However, it is by design more fault tolerant because it's hierarchical. And that's because one or more central servers, if they fail, the others can continue to provide data access to end users. Now, server crashes in a decentralized system may affect the performance and limit access to some data, but in terms of the overall system uptime, the system offers a big improvement over a centralized system. Another advantage of this design is that the access time to the data is often faster, and that's because owners can create nodes in different regions or areas where activity is high. So, however, the decentralized systems are still prone to the same security and privacy risks to the users of a centralized system. And while their fault tolerance is higher, this comes at a price. So maintaining a decentralized system is usually a little more expensive. And lastly, we have distributed systems. So a distributed system is similar to a decentralized one in that it doesn't have a central owner, but it actually takes it a step further. It eliminates centralization completely. So in a distributed system, users have equal access to data through user privileges, and they can be enabled where and when needed. And the best example of a vast distributed system is the internet itself. So distributed systems have evolved as a result of the limitation of the other two. So with increasing security, data storage, and privacy concerns, and the constant need for improving performance, distributed systems are the natural choice for many organizations. And it's no surprise that this technology, using the distributed system, most notably blockchain, are changing many industries. So communication lies at the core of information dissemination and enabling the exchange of data between entities in various domains, from computer networks to telecommunication systems. As a result, communication models have undergone a remarkable evolution, adapting to the changing demands of information exchange by creating more efficient, scalable, and adaptable systems. And each new model has progressively reduced coupling and improved scalability, ultimately addressing the limitations of its predecessor while building on its strengths. And I won't go into a lot of detail here. We're going to talk about the client server, the publish subscribe, and the data-centric publish subscribe model over the next few slides. But I wanted to give you just a kind of a brief evolutionary overview of the different models. But before we get into that, I do want to take a step back and tell you a little bit about DDS, mainly because I'm going to assume that a lot of people on the call really are familiar with OPC UA and MQTT, but the familiarity with DDS may not be as strong. So DDS was actually developed back in the 90s at Stanford University in the robotics lab, and it was meant to remove essentially a distributed solution, to not have any centralized brokers or servers, but allow the coordination of robotics across the network. So the object management group now publishes and maintains the family of specifications, which are based on the data distribution standard. The DDS is a communication protocol. The DDS communication layer is based on a software data bus. And the data bus is a logical thing, not a physical thing. And this runs via a publish-subscribe model. Remember, I said that as each evolution, we take the strengths and build on or improve the weaknesses. So the DDS data bus is essentially a shared global data space where data is continuously flowing to and from its intended and authorized recipients. As you multiply this by hundreds of thousands or even millions of publishers and subscribers. So scalability is something that it's really at the core of DDS. So the DDS standard is a pretty rich standard like OPC. This is about 14 or 15 different parts. But a couple of the main things that DDS focuses on is interoperability. And it does this through the real-time publish subscribe or RTPS wire protocol, which is transport agnostic. So the wire protocol can run on traditional IP, but that's not actually required. It also focuses on portability. So through the DDS language API specification, there are specifications for C, C++, Python, Java, Rust is in the works. So there's a lot going on the language side to make sure that when you're working with a standard, you don't really get vendor lock-in. You can switch between vendors as needed. And then, of course, security. That's supported through an intrinsic plug-and-play architecture that focuses on securing the data. So DDS security is a little bit different than a lot of other securities. And it's not meant to replace that, but it's meant to enhance and make the security much better, moving you closer towards a zero trust security environment. And of course, RTI is fully compliant with the OMG DDS specifications. We sit on the board and we drive a lot of evolution into the standard. So we happen to be a premier vendor of the DDS. So the one thing that really differentiates DDS from the other IIoT protocols is its rich quality of service. Quality of service can really be broken down into three major things. You have events, so those are changes that occur, they're ephemeral. And then there's state, so it's really a single source of truth to the application. Late joiners to a system can get the state, so they don't have to be there to receive the events. DDS makes sure that, just like a database, that everybody is getting access to the most current snapshot And then there's also telemetry. So you can change the periodic rates, the best effort, reliable communication, depending on what the needs of your application are. Like I said, it's a very rich, configurable quality of service settings. So today, data has become a first-class citizen, and that's because it drives decision-making, innovation, and optimization across industries. So data is making it a critical asset for business and organizations to leverage for competitive advantages. So we've reached a turning point actually where the software experience has become more important than the capabilities of the hardware. Now, I'm not saying that advanced software doesn't require advanced hardware. Rather, it's really that strategic combination of great hardware and great software, which is giving end users the most value. And the ability to collect, process, and derive insights from data has become integral to improving efficiency, enhancing customer experiences, and staying at the forefront of technological advancements. Today, there are two protocols that are predominant in the market and are being used essentially to connect device to device and then the edge to the cloud. And while these protocols are really good at what they do, they've got a really good expansive ecosystem. But OPC at the edge, because it is client server based, it actually creates a centralized network architecture. At MQTT, because it is publish subscribe, or a decentralized network architecture. We believe that at RTI that to fully embrace the data and be able to use it to drive the most best decision making, that a fully distributed system with DDS and the data-centric publish-subscribe communication model is really the most flexible architecture, and also for future-proofing. So let me go in just a little bit about the OPC UA. It's a client-server communication model that we talked about before. It's very popular. It is born out of process automation. It pretty much dominates in the industrial space. But it's based on a client-server model. And as we talked about, it introduced a more structured approach with clients being able to make requests to servers for data or services. And it provides centralized control, so it's easy to maintain. It's easy to manage the data. It's easy to manage security and access permissions. But it does have issues around scalability. It has issues around single points of failure. And it also requires that clients need to know the location and details of each specific server. So applications must have a pretty intimate knowledge of the system that they're being deployed to. Now, a lot of this can be managed through configuration done at the commissioning time, but it's still tightly coupled to the knowledge of the network. So the coupling level on this is moderately high, so because clients are essentially coupled to servers. MQTT, another very popular protocol. It's very easy to use. It's born out of oil and gas, came up through the telecom industry. It's very lightweight. There's a lot of support, especially with the cloud, Azure, AWS, Google. They all have solutions for MQTT, for native communication. MQTT, it introduces a level of decoupling over OPC UA by allowing the publishers to broadcast messages to a set of subscribers who expressed interest in specific topics or events. And so again, some of the strengths are, it's a decoupled data distribution, which allows multiple subscribers and publishers to work with direct point-to-point communication. There is, on the limitation side, there's limited support for complex data. And remember, we talked about data is really becoming a first-class citizen. So we need to understand these complex relationships. There's potential message loss and scalability challenges in large systems. And it still requires a central broker or mediator for message routing. And this potentially becomes a single point of failure or a point of non-determinism if you're looking for real-time control or real-time communication. And then the coupling of a publish-subscribe model actually reduces the coupling further by allowing the subscribers to be unaware of the exact location and identity of the publishers. So publishers can move around, and as long as the subscriber is only aware of the broker, it's perfect. So subscribers actually only need to express interest in specific topics and knowledge of brokers used for routing. And the last model that I want to talk about is the data-centric publish-subscribe communication model. And I want to take a quick step back, because if you think of point-to-point, that was really the first communication model, and that is a distributed system in essence. The problem with the point-to-point is that when applications, especially in a bespoke system, have to integrate and communicate with each other, it becomes very complex to manage all this data. And it really comes down to the structure of the data and then the quality of service around the transmission of that data. So remember that I said at each level in the communication model, each evolutionary point, we're taking those strengths and then building on the weaknesses. So where we've evolved to today is what we call data-centric publish-subscribe, or what we call the data bus. So the data bus is really like a logical global data space. So there is no centralized server, and there's no broker. Entities very efficiently communicate with each other, and they use, because DDS is transport agnostic, we use reliable UDP, TCP, multicast, even non-Ethernet ways of transmission. So the protocol itself, because it's not tied to a transport, can be very efficient. Shared memory is another model. Some of the strengths are that it supports complex data relationships, real-time communication, and fine-grained control over message delivery and reliability. So applications really just subscribe and publish to data. They literally know nothing about where the publishers are, where each entity lives on the network. There are some limitations. The complexity in configuring can be a lot sometimes, and actually the technology could potentially over-engineer for simple use cases. And the coupling level on this, though, is very, very low, because as the data-centric publish-subscribe abstracts most of the communication details, allowing publishers and subscribers applications to discover each other by automatically focusing solely on the data that they need. So now I want to take a second to just kind of go over a real kind of like edge to cloud deployment using each communication model. Excuse me. So here if we look at the AMR AGV at the bottom, all the way up to your warehouse management system, and on the side there you see that we're using a nice OPC UA information model. But the challenge is a lot of people, I think when they think about a server, is maybe there's one or two centralized servers. What really happens in this world is most devices and most applications actually come with their own servers. So what you have is like we have here is a myriad of connections that have to be maintained and understood. Now on the application side, when they're writing that's not a problem. They're really just looking at the information model and the data that they care about. But on the management and deployment side, and then maintaining the system while it's running in the field, it actually becomes a challenge. And also we talked about single points of failure. If we lose any server along the way, we can pretty much lose the entire system. Now MQTT, because it's publish subscribe, actually builds upon those strengths of client server. And we can see now the communication coupling is much more reduced, because instead of clients and servers knowing about each other, clients really only know about the brokers. So, each application subscribes to the topic that they're interested in, and they do that they have to specify with a specific broker that they want to go to. So this actually makes things a lot easier when it gets to the deployment side. And you can see as well, MQTT speaks in topics, so you describe the data that you need. But we still have potential for network overload you have the potential for not so much a single point of failure. So if part of the system goes down, it can keep operating, but it can be critical. And then building upon those strengths and looking at the weaknesses, if we look at the OMG's DDS as a data-centric publish-subscribe, it's really this data bus structure. Now, again, I want to be very clear and point this out, that the data bus it's a logical thing. People always ask where it lives or what protocol it is, but so what we're showing here is a logical structure, because the middleware actually manages underneath the floor. There's automatic discovery, so entities discover each other automatically, and you can fine tune that. It can work on a LAN, on a WAN, across the internet. It's also, if you look at the side, we talk about a unified data model. So where the information model describes the relationships of essentially devices and entities that you're looking for, and then the topics in MQTT actually give you a little more structure of what the data looks like. The DDS data model is actually a very strongly typed data model. So entities must, that go to or exchange information with each other, must actually be using the same data types, right? So it enforces a very strong typing system, so that instead of just a string specifying your type, you're actually saying that this is a float or an int, or actually this is a complex structure or union of information, and then DDS sends that information around in the most efficient way. So we have talked a lot about features and functions and some performance. Now I want to talk a little bit about security. As we said, security is paramount importance in AMRs due to the potential risks and vulnerabilities associated with their operations. AMRs often work in dynamic environments, including warehouses, factories, and hospitals, and where they interact with both people and other machines. So ensuring the security of these systems is essential to prevent unauthorized access, tampering, or malicious attacks that could disrupt operations, compromise data, or even pose physical safety risks. So furthermore, as AMRs may carry sensitive data and operate autonomously, robust security measures are necessary to protect against data breaches, unauthorized control, and ensure compliance with privacy regulations. So by prioritizing security, AMR operators can safeguard their assets, maintain operational integrity, and build trust in the technology's reliability, making it a foundational element in the successful deployment of an AMR system. So here on the right, I just want to go through this real quick. We see encryption, authentication, access control, security logging, and lifecycle management. And you see that the DDS has all green. And then OPC and MQTT have green, yellow, and red. And what I want to point out here is what that means is that's not to say that certain vendors don't offer those features or functions. It just means that they are not actually part of the standard. So with the DDS, to be fully compliant with the OMG's DDS standard, be a compliant vendor, you must meet all of this criteria, and that's all defined within the standard. So this ensures interoperability across vendors. I can use vendor A and vendor B and still get very detailed security logging and lifecycle management of my certificates and stuff. Again, I just want to point that out. This is really looking at it from the standards standpoint and not from a vendor standpoint. So I want to jump back here real quick, because in the beginning we talked about network architectures. And there's a couple things that I didn't really point out. But if you look, we said that distributed systems provide the best fault tolerance, the best scalability, right? And decentralized and distributed really support the future-proofing of a system. But with a distributed system, maintenance and development do come at a premium, typically. And this is going back to that whole idea of point-to-point communication when end users had to manage and do all this on their own. But the interesting thing is that the DDS standard is that it actually allows you to move that, because it manages all of that quality of service and all that interaction and orchestration between the different publishers and subscribers, the data-centric publish-subscribe approach actually reduces or lowers maintenance and development costs. So yeah, I just want to leave you with that. So I want to do a real quick security demo. And because we are an IIoT protocol vendor, we do have a lot of customers in this space, but we don't really make these things. So we've put together just a small demo for you, just to kind of give you an idea of a few of the security features that DDS supplies. So what I want to show you here is just a very small AMR system. We're going to have 4 AMRs. And since we're using ROS, and ROS uses DDS as its middleware, we're actually going to use the ROS2 RViz to see what's going on. We have a tiny little system monitor, so we can just show a little bit of data. So you can see that, as they move around, you'll see the data change. And I already said we have 4 simulated applications that are publishing into this logical data bus. So I just want to show you this for a few seconds. You can see they're moving around. Again, we're not an AMR vendor, so we put together a nice little demo just to show you. There's no path planning or anything like that, but just so you can see the things communicating with the different entities within the system, or the AMRs communicating with the visualization tool, and then our little UI. So next, I want to show you is the exact same demo, but this time we're going to turn on a little bit of security. So the RViz app and the system monitor only have access rights to be able to subscribe to the data. So in this one, we're actually going to try to publish some data from the system monitor. And what's going to happen is we're going to see some logging where DDS actually rejects that. Yeah, what I want to highlight here, just real quick, is as the monitor is going to create a publisher, we can see that the endpoint is not allowed because he doesn't have the right access privileges. So this is actually a little bit better than just encrypting the data. The data, of course, is encrypted as well, but now there's access rights being brought into it, and the policies govern that this monitor is read-only. So if it tries to actually publish data into the system, the global data bus is not going to allow that to happen. So we're going to do one more quick demo, but this time we're going to do with an intruder. So everybody's subscribing to data, the AMRs are publishing, and this one we're going to show you that DDS won't even allow discovery to happen. So DDS is able to discover that an intruder is coming in. And since that application doesn't meet the system's security requirements, it just won't be able to join the system or receive any data. So the system actually appears invisible to the intruder, as all discovery data is also encrypted. However, the system is able to detect the intruder. It'll print out a log message over DDS. So a security expert would be able to see this in real time through the DDS logging. Yeah, so you can see in the upper left-hand corner, bring it over. Now the intruder is launched, but it wasn't able to actually discover any of the other entities within the system, and because it does not have the rights, the right policies. So this is a huge advancement, I think, for security. In a really, DDS has taken a really good approach to helping solve the security problem for the industry. So, how the protocols meet the requirements. So again, I want to make sure that I'm clear on this. That here I'm actually talking about the standards. Right? I'm not talking about vendors who are implementing the standard. This is really just about the standard itself, and then also the the communication model and the network architecture. We can see there are many other requirements as well. Just chose a few of the top ones that we thought were really important to AMR development. But you can see that all protocols get around reliability and interoperability and standards compliance. They all get good marks. Security is a little bit touchy because it may just focus on encryption, or in the case of the MQTT specification, part 5, it actually describes the security as non-normative. So again, vendors may implement great stuff, but the standards, because it's not defined there, it kind of makes it a little bit difficult for potential interoperability across a heterogeneous fleet in the future. So in summary, it's just not as easy as picking a protocol. There's a lot of things that you have to consider. It really comes down to the important characteristics of the system that you're interested in. You have to have the right network architecture. That's critical. We believe a data-centric approach before supporting a distributed network architecture is essential for all modern systems, especially because you're crossing organizational boundaries, edge to cloud. And selecting that right communication model is essential to be able to implement that network architecture that you choose. And security is absolutely vital to the overall solution to safeguard data and devices from threats and vulnerability. So with that, I want to say thank you, and then we'll turn it over to questions.
Yeah, so thank you, Mark, for the presentation. We can now address some questions that I see in the chat. Let me read the first one. It is, MQTT uses topics. Doesn't that make it data-centric as well? You publish and subscribe to topics.
Okay, that's a great question. So MQTT, it does use topics. The topics in MQTT are actually string-based, though. So even though you're describing the name of the variable and it has a mechanism to allow you to show a hierarchy, which gives you the relationships, you really don't have any type information. So if I'm subscribing to some sensor value, I don't know what type of data that is. I don't know what any quality of that data. So it's hard to enforce any kind of strong type safety on that. Because MQTT is actually missing a type system. And that's one thing that you need to be able to be data centric, because you have to understand the data. More than just what it looks like on the wire, you actually have to understand what it converts to in the world of an application.
Perfect. The second question that I see, it is the OPC UA information model describes types. Doesn't that make it data-centric too? Pretty similar to the first one.
Yeah. No, so again, it's now OPC UA is a little bit interesting because when you describe an information model, you can describe the type, but really, and you do when you're describing like a value or and then you're expressing relationships between these. The focus in OPC is really about being able to express relationships, and the type information is there to be able to transmit, for discovery. And also, being able to observe a system dynamically, but that doesn't actually propagate up to the application level. So applications actually have to know the types in advance. And then if I go to the server, say I have a sensor and I say that's like a 32-bit float, that's what it's defined on the server. And then I go to the server because I upgrade my sensor and I have a 64-bit float. So I may change that in my server, but now there's a type mismatch, and the system doesn't know how to, the application won't know how to access or get that value. So we're something like a DDS where there's true introspection built in. I actually don't even have to know the type up front. I can learn that type as it's coming across and adapt my application dynamically to that. Or, I can use it to have like an evolving data model. So maybe if I change types or something, I don't want my other applications to use that data. So it allows me a much better way of managing the types within the system. So no, it's not quite data centric either.
Thank you so much for answering these questions. I don't see any other comment from the chat, so we may have come to an end. Thank you, Mark, for the presentation, for answering the questions and the demos. That was an interesting one. And thank you to our audience for joining us today. Those questions that you may have sent and we have not answered, we will follow up via email after this webinar. And finally, this webinar will be available on demand through the same registration link. So thank you so much for your time today and have a great day.